All right, let's talk about 4.3 here, logarithmic functions. So, what is a logarithmic function? A logarithmic function is for any x and b that are greater than 0, with b greater than or equal to 1. We say that a logarithmic function is a function of the form f of x equals log base b of x. We call this a logarithm with base b of x, and that is read, again, log base b of x. Log base b of x. And we'll get to what that means in just a moment. If we say that y equals f of x, so if we just come up here and we say, well, all of this is also y, then the logarithm y, which is log base b of x, is the exponent to which b must be raised to get x. That is, y equals log base b of x means the same thing as b to the y equals x. And that's very much worth writing out. So y equals log base b of x is equivalent to, that's what this double-headed arrow means, it's equivalent to b to the y equals x. And you'll see it a lot explained using this sort of arrow thing, but it says that you can say that b to the y equals x. You see that a lot. It's often written actually backwards from this, in fact, as log base b of x equals y, so that you can look at this a little bit more normally, because we read from left to right in English. You say b to the y equals x. That's what that means. B to the y equals x. It's the exact same sort of relationship. It's a different way of writing things. And actually, logarithms are a multiplicative way of counting. And there's a video that I'll show you all that explains this better than I can in video format, at least. I usually do it in my class. But note further that b is called the base of the logarithm. The domain is all positive real numbers, all non-zero positive real numbers, and the range is everything. So you can get anything out of a logarithm, but the only thing you're allowed to plug in are numbers strictly bigger than 0. Now, any number bigger than 0 that you want to plug in, you can. Note also the restriction on the base. The base also has to be a positive non-zero real number, also not 1. So log base 1 doesn't exist, log base negative number doesn't exist, and that'll make a little bit more sense when you see the additional video. But for now, keep all of that in mind. So this is read f of x equals log base b of x, and what it means is it is f of x is the y, it is the number, f of x is the number to which you raise b to get x. It's just a different way of looking at a function. And we'll talk more about the relationship between this function and the exponential function in a future video, but spoiler alert, they're inverse functions. If the exponential was the square function, then the logarithm would be its square root. They are inverses. They mutually annihilate one another, and we'll talk about that in more detail in the future. But for now, let's move on. So let's see if we can't do just a suite of 3 examples here real quick. The first one is, what is the value of log base 9 of 81? So we read this log base 9 of 81. What this question is asking, very simply, is if you're counting in a times 9 kind of way, how many steps do you have to get to 81? So you can think about it in a couple of ways, and I'll show you these ways. This is the less conventional way to think of it, but think about it this way. You start here at the number 1. And what you're going to do is to hop from any point on this timesy counting number line. You're going to multiply by the base. So you're going to do a times 9. So 1 times 9 is 9. Okay? And then if you do it again, you multiply by 9 again. 9 times 9 is 81. The question is asking for this red value up here, okay? Here you've taken 0 steps. Here you've multiplied once. Here you've multiplied twice. Log base 9 of 81 is this number. It says base 9, that's how you're counting, of 81. How many times do we have to multiply by 1 by 9 to get 81? That's what this is asking. That's the number line. Except instead of adding, like you normally do on a number line to get from point to point, we're multiplying to get from point to point. So we've went an order of magnitude above. The other way to think about this is just set this thing equal to x. So here's another way to think about this. You say log base 9 of 81 equals x. And then we just read this like we used to. Another way to write this would be 9 to what power is 81? What number do you have to raise 9 by to get to 81? Or how many times do you have to multiply 9 by itself to get 81? Well, twice. So then we'll say that log base 9 of 81 is 2. You would just type in the number 2. That would be it. You would say log base 9 of 81 equals 2. That's how many steps you have to do that. Let's look at another one. And I welcome you to pause the video, as always, and give this one a shot. So we're going to do log base 4 of 16. So how do we think about that? So again, let's do this again. Okay. So we're going to do this. You start down here at 1, and we're going to count in a times 4 kind of way. So we're going to count in a times 4 kind of way. So 1 times 4 is 4. And then 4 times 4 is 16. This time it's the blue number we're looking at. Here you've went 0 steps. That's where you started. Here you've multiplied once. Here you've multiplied twice. Log base 4 of 16 is the number of steps it took you when multiplying in a times 4 kind of way to get to 16. That's all that we're talking about. So then we say that log base 4 of 16 equals 2. The boring way to do it is to rewrite this as a exponential. We say log base 4 of 16 equals, and it doesn't have to be x. Choose any power you want to. I don't care. J. Why not? We're saying that 4 to the j, we cross back over the equals 16. So 4 to what power j is 16? Well, 4 times itself twice gives you 16, so j must equal 2. So that's your answer. Log base 4 of 16 is 2. You can either reframe the question, or you can think about it in terms of number lines. And then I want to look down here real quickly at this one. What is the value of log base 3 of 3? Okay. So on the number line, what we're thinking about is something like this. We're thinking, okay, well, we're going to start down here at 3. Start down here at 1, rather. And we're going to count in a times 3 kind of way. So I'm going to count times 3. 1 times 3 is 3. Now, we're multiplying, so we start the number line on the multiplicative identity, 1. If you are doing a normal number line, like multiplication, we start with its multiplicative identity, its additive identity, rather, which is 0. That's why we count that way. But if you're at 0 steps here, where you start, you're at 1 step when you get to where you want to go. And you can see pretty clearly that if we change this to log base 4 of 4, or log base 12 of 12, or log base 42 of 42, if you start at 1 and you multiply once by that number, and that's the answer to this, that's always going to work out that way. In fact, we'll get the property that log base x of x is 1. It'll always take you 1 step counting that way to get there. But you can also just reframe this question if you want to be boring about it. Sure, let's do that. Why not? You can say that the log base 3 of 3, set it equal to some number. I don't care. Z. So this is 3 to the z equals 3 is another way to write this. 3 to the z equals 3. So 3 to what power equals 3? What number do you have to raise a number by to get itself back? Well, clearly, z must be 1, and that's what we were talking about. These are thinking problems, and they do get a little bit harder than this, but by and large, that's kind of what logarithms are talking about. Let's talk about some other examples. So let's make this a bit spicier. Let's do this with fractional logarithmic inputs. What is the value of log base 4 of 1/2? So let's reframe the question that we were previously thinking about. If a number line for your logarithm is asking you to count in a times 4 kind of way to get to 1/2, and we start at 1, let's look at this. Let's start at 1 right here. Now, clearly, if we count in a times 4 kind of way this way, our numbers are going to be 4, 16, and so forth. We're actually moving away from 1/2, which is the value we're trying to get to. So let's think for just a moment about how we can reframe this and how we might get to 1/2. If the numbers get bigger when we go right, well, notice how much space I left over here to the left. What happens if we instead go to the left? So here's what happens. If we did a times 4 to get to 4, and we did a times 4 to get to 16, you could think about going backwards as dividing by 4, if you wanted to. And so let's take a look at that. Log base 4 of 1/2. So let's go back one step and see what happens here. So in order to continue this pattern, we have to come from whatever this number is by multiplying by 4. So what number times 4 is 1? Literally, what number times 4 equals 1 is the question. Well, to solve this, you just divide by 4, you get 1/4. So this number must clearly be 1/4. So let's take a moment and just think about what's going on here. Look at this and try and figure out, because 1/2, that value is clearly somewhere in here. So what do you think this value exactly is? This value, 1/2, somewhere between 1/4 and 1, if here's the number of steps. You went 0 steps at 1, that's where you started. You went 1 step here, 2 steps here. This value would be -1 steps. You went back in time 1 step. What do you think this value here would be? And if you give it some thought, it should make sense that this is -1/2. Neat. But let me show you a robust way to figure this out. If you want to use some algebra, that's the intuitive way to think about that. That is a -1/2 step. That's the number halfway between these two. Thinking about this way, it's halfway between these in terms of stepping. It is stepping back instead of a times 2 to get here. It's a times, instead of a times 4 to get from 1/4 to 1, you multiply by times 2 to get between here, is what I'm saying. That's a times 2, and then a times 2 again would get you there. It's the same thing as that whole times 4 is what I'm saying here. And 1/4 times 2, would give you a -1/2. So let's think about that. So let's look at this. You can reframe the question using the same sort of logic that we've used before. Log base 4 of 1/2, okay, and then just set it equal to something, may as well be x. And then you can reframe this. So you can write this. It's the base, okay, to the thing that it was equal to equals the thing inside the logarithm. And now what you need to do is read this. It says, what power of 4 gives you 1/2? That's what it says. So we need to find a common base between 4 and 2. We need to write both of these things a little differently. So we're going to come over here, and there's a common base between these two. So I'm going to leave the left-hand side alone for a moment, and we're going to work with this 1/2. I hope that we agree that we can write this as 2 to the -1st power. 1/2 is 2 to the -1st power. It's the same thing. So our base is 2, and I can write 4 as 2 squared. So instead of writing 4, I write 2 squared, like this. Close that up to the x. So all that I did was, instead of writing 4, I just wrote it as 2 squared. And it's still raised to the x power, and I rewrote 1/2 as 2 to the -1st. because that's how negative exponents work. In general, something to remember is if you have some base b to the negative x, that's just 1 over b to the positive x. That's all that means. It just makes it positive, but in the denominator. So we've got this to work with so far. So from here, we just use some laws of exponents. We say that when we raise a power to a power, we multiply. So this is 2 to the 2 times x, 2x, equals 2 to the negative first. And then if you have the same base, which is why we got the same base, then you can just set their exponents equal. The only way for these things to equal each other is if the exponents equal. So we're going to say 2x equals negative 1, and then we're just going to divide both sides by 2 and get x equals negative 1/2. If you would rather do the math on this. Completely up to you which way you want to do this, thinking about it or doing the math, but we'll do another example and think about it. Remembering sort of how that last one was handled, let's take a look at this one. And this time I'm going to do it the algebraic way first and then show you on a number line the way to think about this. So let's just go straight into the algebra on this one. And of course, as always, pause the video, give it a shot, see if you can figure this out on your own. If you can, awesome. Log base 16 of 1 over 64. Okay, so clearly, since the base is bigger than the number that you're taking the logarithm of, you should get a negative answer because you have to go back in time. Think about our last example. We're going to set this thing equal to x, or j, or k, or a. I don't care what you set it equal to. And we're going to solve it. So we're going to reframe the question. So it's the base, which is 16, all right, to the thing that it's equal to, equals the thing that you're taking the logarithm of. Look back at the definition at the very beginning. Look back in your notes at that. And what we're now going to need to do is rewrite both sides with a common base. So all that we're going to do here is either try to write them as both base 16 if we can, but we won't be able to pull that off. So instead, let's try powers of 4 this time. I'm thinking 4 raised to some power probably is 64, or we may even be able to pull this off with 2's. 4's might be easier, 2's might be easier for you, I don't know. Let's do it with 2's. So 16 is 2 to what power? Well, let's see, it's 2, 4, 8, 16. So 2 to the 4th is 16. So instead of writing 16, I'm just going to write 2 to the 4th. I'm going to slap it in some parentheses, and it's still raised to the x. These left-hand sides are still equal. Equals. Okay. And then this will be, and I'll do one extra step for you this time. 1 over, and 64 is 2 to what power? I'm trying to get a common base so that I can just set their exponents equal and solve some basic algebra stuff. So 64 is 2 to what power? Let's see, it's 2, 4, 8, 16, 32, 64. So it's the 6th power. So it's 2 to the 6th power. So that's what that thing's written as. So we can instead write this as 2 to the 4x. When you raise a power to a power, you multiply. And then 1 over 2 to the 6th is just 2 on top to the negative 6th. I'm just using that property that I showed you earlier. Now, the bases are exactly the same. That's why we did all the math that we did, and we just got the bases together. And now we're just going to say, well, that must mean that 4x equals 6, or 4x equals negative 6, rather, or x equals negative 6 over 4, or if you prefer, negative 3 halves. And I do prefer negative 3 halves. So there we go. That's all there is to that, negative 3 halves. So log base 16 of 1 over 64 is negative 3 halves. But what does that mean? What does that mean? That's completely contextless, and a lot of professors don't bother showing any of this when you get into college. But I'm going to go ahead and show this. And I know that counting forward isn't going to help me very much. Remember, this is logarithmic number line, so we're going to start with a 1, our identity element for multiplication, and we're counting by 16s. All right, so we're counting by 16s, and maybe this was lost in the last example. So if I count in a times 16-y kind of way, I get to 16 pretty clearly, but I'm trying to get to 1 over 64. And 1 over 64 is never going to be reached if I go right. So I'm going to have to go left. Now, you may notice that, and this isn't to scale, but you may notice that if I go left and I multiply this way, I can get, let's try it here. Let's see, what number do I have to multiply by 16 to get 1? That should pretty clearly be 1 over 16. So this is just 1 over 16. Okay, positive 1 over 16. All of these numbers will always be positive forever. And if you want to know, obviously, how to go backwards, I want to always read this going right, but it's pretty clear that this is also just dividing by 16 if you want to read it backwards that way. Okay, and if I want to go back again, another step, I will divide by 16 again. So I can divide this by 16 again, and I get some really strange number. Specifically, 256. You'll get 1 over 256. If you do the math. If you do 1/16 divided by 16, that's 1 over 16 times 16, which is 1 over 256. Okay, clearly that's smaller than 1 over 64, the number that we're trying to get. So let's maybe not go back that far. So here's where you start having to think about this in terms of little jumps. So watch this. Maybe that was too far. So let's go back in time for a second. Okay. And let's say that this is the 1 over 256 number. Okay. So if I come from here to here, that's times 16. And if you don't believe me, 16 times 1 over 256, or 1 over 256 times 16 is 1/16. Look it up on your calculator. The number 1 over 64 lies somewhere in here. We don't know where it lies at, but it lies somewhere in here. So maybe instead of jumping by 16s, we can jump by some other increment. So maybe we can jump by 2s. That's what we did in this example. And we could get away with jumping by 4s here as well, but I'm going to jump by 2s because that's what we did over here. So I'm just going to come back this way, and I'll show you both ways, multiplying and dividing. But coming from 1 over 256, if I'm counting in a times 2 kind of way, if I count in a times 2 kind of way right there, I get 1 over 128, and then I times 2 again, and I get 1 over 64. And I'm just going to, just for the sake of completeness, I'm going to do this, even though that's the number I'm looking for. I get, if I multiply in a times 2 kind of way again, I get 1 over 32. And then if I multiply in a times 2 way again, I get 1 over 16, and I'm good. So we broke up this 16 as 4 times 2 jumps, because 2 to the 4th equals 16. You can do 4 times 2 jumps, and that's the same thing as 1 times 16 jump. So I just looked at that way. Now, if you want to think about it going backwards, since we were able to get to 1/16 pretty easy, and think about dividing by 2 this way, and then think about dividing by 2 again this way, and dividing by 2 again this way, and work backwards instead of doing what I did, that's fine to think about it that way too, but I don't want to clutter up this number line with too much stuff. So the question is now, how many skips x did it take, counting in a times 16 kind of way, to get to 1 over 64? That's what this question is asking. So we start at 1, and we go back 1 entire step, right? So that's 1. Okay. If we go all the way to 1 over 256, that's 2. And what we did was instead went halfway. This is 1/2. This is 1/2 of a step. This is 1/2 of a step. The number, this is -1 step, this is -2 steps. The number halfway in between -2 and -1 that goes over this is -1.5, or -3/2. And that's it. And if you want to, you can even count the entire way back in times 2 kind of ways. If you wanted to, you could look at it this way. Look, we can go all the way up to 1 like this. Here's the numbers. I have to write them on top because there's stuff in the way. But 1/16, the next one is 1/8, then 1/4, then 1/2, then 1. And you can see pretty clearly that if you're going between these, that's times 2, that's times 2, that's times 2, and that's times 2 to get there. So if you have it working like this, all that I'm saying is if you have it working like this, Watch. How many steps do I have to take? I'll do it in white. I take from 1, 2, 3, 4, 5, 6 steps. I take 6 steps backwards, and I'm counting overall. And what we had done was divided each one of these into 4 different parts. And that gives you this -3/2 that you got earlier. So that's how we get this number. Look, we divided our normal jump of 16 into 4 times 2 parts. That's where that number comes from. Now, maybe that's a lot to think of, and this work over here is a little bit easier to do, but I do want you to see exactly what it is you're doing on a number line as you do this. Let's move on. So, here's another way that we can ask these sorts of questions. What is the positive value of x in the equation log base x of 256 equals 8? And if you know the basic way to rewrite these things, this thing is super easy, barely an inconvenience. Watch this. We say that log base x of 256 equals 8 is the same thing as take the base, raise it to whatever is on the other side of the equal sign, and then set that equal to whatever was inside of the logarithm. So pretty clearly, what we're going to do is we're going to take the 8th root of both sides to solve this. So let's take the 8th root of both sides to solve this. So when you take the 8th root of this side, you get 8. Let me just write the whole thing out. You get the 8th root of x to the 8th equals. Now, when you take an even root, you technically get plus or minus the 8th root of 256. Because you took an even power, you have to take both the plus and minus. But I asked for what's the positive value. So I only want the positive value. So we didn't need to actually write that. We can just say the 8th root in this case of 256. Okay. Now you can rewrite this as the 8th root of x to the 8th is x, of course. And then this is 256, sorry about that. This is 256 to the 1/8 power, if you want to think about it that way. But the 8th root of 256 is asking the question, what number do you multiply by itself 8 times to get 256? And in fact, this is a good time to look at this. This is actually asking a question about exponentation like this. Look at this. This is exactly the same sort of thing that we've seen in logarithms. You've seen this kind of behavior before. Logarithms are just restating what an exponential is asking. Square roots are just restating something that an exponential said. This thing right here is saying the exact same thing. The exact same thing as the 8th root of 256. In just one little thing that we stated, we set an entire equation, and in order to solve this, you would just pick some variable to set it equal to, raise each side to the 8th power, and then you would be back in a normal quadratic or not exponential form, a polynomial form, a monomial form. So the thing that we're doing with logarithms and exponentials is just a heightened version of this. It's the same, it's just math behaving in the same sort of way. But this is asking what number times itself 8 times is 256. And you'll find that if you raise 2 to that power, if you raise 2 to the power of 8, you get 256. So the 8th root of 256 is 2. So log base 2 of 256 is 8. So we would say that x equals 2. But it's just using the same properties as before. Let's look at another one. So imagine that you were asked, what is the positive value of x in the equation log base 9 of x equals 2? Okay? Log base 9 of what number gives you 2? Okay. This is different than some of the other ones that we've been done, but we need to just solve for x. No big deal. Let's look at this. So we rewrite the question, log base 9 of x equals 2. Be very careful. Okay, we'll rewrite this. It's the base to the thing, to everything that's over on the right-hand side, equals whatever was on the inside, like that. Well, pretty clearly, we just solve here, and 9 squared is 81, so 81 must be x. So that's it. That's the positive value. It's 81. Good job, we solved it. That's all that there is to these sorts of things. Just rewrite it and solve it. These are the easiest things to solve. All right. We're starting to get a little spicy here, but we can do this. So, let's write log base x minus 6 of 2 equals 9/5 as an exponential equation, but good news, we don't need to solve it. We'll get to that later. But for now, we're just going to rewrite that. And as always, and let me make this dead clear with some colors here, it's log, okay, and then the base. So the base in this case is x minus 6, okay. It's of 2, the number, okay. It equals, and then it equals 9/5. It's going to be rewritten like this. It's going to be rewritten as the base, whatever that was, slap it in some parentheses, okay? Slap it in some parentheses. It wasn't the problem, too. Okay. 2, literally whatever's on the other side of the equal sign, all of it, equals whatever was inside of the log. It will always look like that. It's just reshuffling things into exponential form. And that's it. Now, we can solve this if you wanted to, but if this were the question, you would type in that equation and be done. If you wanted to solve this, you would raise each side to the 5th power. To get rid of that over 5 part, you would take the 9th root of each side and then add 6, and you would be done. So, whatever you want to do with this after this is up to you, but if the instructions say don't solve, don't solve. This is definitely something that we can solve using what we know, but that's not the point. The point is, can you rewrite this no matter how ridiculous it looks? And the answer is, well, yeah, you can. So now for the last one. So what this one's asking us to do is to write, what? What does that say? Oh, that's new. Okay. There's no base here. How do we do this? What does that mean? ln. What does that even mean? Is that even an L? Is it a 1? Did Mr. Bryant make a typo? No. That's called the natural log. And what this means is this. So here's a good place to write this down. But this is read the natural log of x. This is read the natural log of x. And all that this means is this is the log with the base of e. That number that's 2.718, about, that occurs from that compound interest formula that we talked about. The base is e. If it says ln, the base is e. This is called the natural base. E is called the natural base because it's the base of the natural log. The natural log of x, ln of x, the natural log of x. It means log base e. That's what it means. Write this down. Definitely commit this to memory. It shows up all the time. So let's rewrite this. So we know that the natural log was log base e of this polynomial, x squared plus x plus 10 equals 3. So that's what it says. It's the exact same thing. Natural log here, log base e, it's the same thing. We always prefer to write it this way. In fact, log base e comes up so often that we made up natural log, ln, just specifically so, we could not have to write this construct over and over. Because mathematicians are, if nothing else, lazy. But it's the exact same thing as always. We write whatever the base was to whatever was on the other side of the equal sign, and you set it equal to everything that was inside of here. X squared plus x plus 10. Okay? It is always the exact same thing, guys. It's always literally everything that's in this box. Put it in parentheses if you have to, if it's more than one term, goes there. It'll be raised to literally everything over here. Everything. It doesn't matter how much stuff's over there. It all goes in the power up here. And then finally, everything that is inside of the logarithm, whatever base it is, goes over here. It is literally a fill-in-the-box problem every single time. You just rearrange the stuff and it's done. That's all that there is to this. We could solve this if we wanted to. This is just a quadratic. You've got a billion ways to solve it. It's got a very nasty constant, 10 minus e to the third, but whatever. E to the third is just a number because e is just a number, and a number raised to the third power is just another number. That being said, this is the last of the examples, so go forth, learn a thing or two, ask good questions when you have them, and I will see you again in the next video when we graph these things.